Hello there and welcome back to the Science Sleepy Minds. You're standing at the edge of nothing. Not darkness, not silence, just pure absence. No time, no space, no ticking clock. Then, in an instant, you wouldn't be able to measure even if you tried. Everything changes. A flash that isn't a flash because light hasn't sorted itself out yet. Expansion without direction. Energy without shape. It's the Big Bang, and it's the first time the universe even considers having time. But let's be clear, you probably won't survive this. Not because it's violent, though yes it is, but because your very existence is tied to things that haven't been invented yet. Like atoms, or rules, or time itself. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And tell me, where in the world are you listening from, and what time is it right now locally? Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You float through nothing, and then, bang, time begins. But not like you know it. In those early femtoseconds after the Big Bang, time isn't divided into hours or even seconds. The whole concept of a second is laughably large here. At this scale, the smallest unit of meaningful time is called Planck time, and we'll cozy up with that brain melter a little later. But for now, you're just watching everything unfold. Imagine a stopwatch starting with no one there to press it. This isn't an explosion in space, it's the rapid expansion of space. Time and space stretched together, tangled up in the newborn fabric of reality. There's a seething chaos of particles, radiation and pure potential. It's hot, absurdly so, like 10 to the 32nd Kelvin hot, which is the kind of temperature that would instantly evaporate your metaphors, along with your bones. Not that you have bones yet. In this fragile moment, the ticking of the universe's clock doesn't come from gears or quartz or buzzing electrons. It comes from change. Time, in the most primal sense, is just a record of things not staying the same. But wait, what is time? That's the slippery fish. According to some interpretations of physics, time might just be our way of understanding motion and causality. Others argue it's baked into the universe, like an invisible conveyor belt pulling everything from past to future. Historians still argue whether early human societies truly conceived of time as linear, or if they saw it more as a recurring cycle, like seasons, tides, and taxes. And yet, the universe keeps evolving. Moments accumulate. Particles cool and settle down into familiar roles. Electrons, protons, atoms. Light is finally allowed to travel freely, about 380,000 years in, which in universe time is practically the blink of an eye. This moment, when light stops getting slammed around by plasma and starts journeying through space, is still visible today. It's called the cosmic microwave background, and we'll spend some quiet time with it soon. But for now, know this. It's one of the universe's earliest timestamps, still echoing across space like a cosmic lullaby. But don't get too cozy. Time hasn't stabilized yet. In fact, the laws of physics themselves are still ironing out the kinks. Gravity, electromagnetism, and the nuclear forces begin to differentiate from one another like siblings moving out of their childhood home. Each of these forces will shape how time works in their domain. Some theories, particularly in quantum cosmology, suggest that before the Big Bang, time as we know it may not have existed at all. Instead, there may have been a sort of timeless quantum soup, a pre-clock state where cause and effect just kind of shrugged at each other across the void. Or maybe there was another universe before this one, and ours is just the latest in a long line of cosmic reruns. No one really knows, and here's where it gets deliciously confusing. If time started at the Big Bang, then asking, what happened before, is kind of like asking, what's north of the North Pole? The question itself breaks the rules of the game. Still, ancient civilizations took a crack at it. The Babylonians mapped the heavens with meticulous care, trying to pin down the rhythms of the cosmos. The Egyptians linked their calendars to the flooding of the Nile. and one ancient Hindu cosmology envisioned the universe expanding and contracting in great breathing cycles, each lasting billions of years. A surprisingly modern-sounding idea for something written down in Sanskrit. Now, as the universe continues to unfurl, time gets less chaotic. Clocks aren't invented yet, but celestial bodies begin to move in ways that will eventually let us invent them. The first stars burst into life a few 100 million years after the Big Bang. Galaxies swirl together, gravity sculpts order out of the early soup, and you start to see patterns, measurable things, regular pulses. Somewhere, billions of years later, you, a tiny primate with a tendency to lose your car keys, will take those pulses and turn them into seconds, minutes, and calendars. But right now, time is still raw and wild. It's the beat of the universe expanding, the rhythm of atoms forming, the heartbeat of entropy waking up. And speaking of entropy, just remember, from the very beginning things tend to go from ordered to disordered. It's the universe's version of why bother cleaning your room when chaos is inevitable? Entropy doesn't rewind. It's one of the few things that actually gives time an arrow, pointing away from the Big Bang and toward whatever comes next. You might think of it as the universe's most ancient clock. Not one that ticks, but one that drifts. So here you are at the very first beat. Not a clock on the wall, but a heartbeat in the cosmos. And while you drift through the afterglow of creation, just know you haven't aged a second. Because seconds haven't been invented yet. You open your eyes again, figuratively of course, because you still don't have a face, and suddenly time has standards. Gone are the chaotic pulses of primordial change. Now, the universe starts to favour consistency, precision, rhythm. Somewhere along the timeline, humans arrive and promptly decide they need to measure everything. That includes time. And no offence, but you're not very good at it. Not at first. You try using shadows. You try watching the stars. You even invent entire mythologies around the rising and setting sun just to make sense of the hours slipping past. But it's not until you stumble upon atoms, those jittery little particles that just can't stop vibrating, that you finally get a clock accurate enough to make even your microwave proud. Welcome to the age of atomic time. You're living in a world where you can split seconds into nanoseconds, then into picoseconds, and still not blink fast enough to keep up. Deep underground or tucked away in national labs, devices hum quietly as they measure the passage of time by counting the ultra-predictable oscillations of atoms, particularly cesium-133, the MVP of timekeeping. Here's how it works, and don't worry, we'll whisper. Cesium atoms naturally vibrate at a frequency so stable you can practically set your existence by it. In fact, the official definition of 1 second is exactly 9,192,631,770 transitions between energy levels in a cesium-133 atom. That's not a rounded number, by the way. That's the actual count, because apparently physics has no chill. Now imagine billions of those vibrations being counted inside a room you'll never visit, probably surrounded by scientists in fleece vests, all while satellites above your head quietly sync up with it. Yes, GPS, the thing that tells you which lane to be in when you've already missed the exit, relies on these atomic clocks. Without their precise timekeeping, GPS satellites wouldn't know where they are, and in turn, wouldn't know where you are. Even being off by a few nanoseconds can throw your location off by several meters. So the next time you find the nearest taco truck at 2 AM, thank a cesium atom. But here's the weird part. Atomic clocks don't just measure time, they define it. They're the benchmark, the international standard. If your smartphone's clock is off by even a fraction of a second, it gets corrected by signals from these atomic overlords. Which means, in a way, your phone is constantly apologizing to science. Still, we didn't get to atomic clocks overnight. Back in the 1940s, physicists were only just figuring out how to use microwaves to provoke atoms into giving up their secrets. The first cesium-based atomic clock was built in 1955, and it was accurate to within 1 second every 300 years. Not bad, considering your kitchen timer is usually wrong by about 2 minutes this week. Modern atomic clocks, though, they're terrifyingly precise. The best ones today won't lose a second for about 30 billion years, longer than the universe has existed. Which begs the question, if a clock is that accurate but no one is around to outlive it, does it matter? Well, kind of. These ultra-precise clocks are now sensitive enough to detect changes in gravity, speed, and even altitude. That's right. If you take your atomic watch up a mountain, it'll tick slightly faster than it did at sea level, thanks to Einstein's theory of general relativity. The higher up you go, the weaker gravity's pull, and the quicker time slips by. So technically, astronauts on the International Space Station are aging slower than you. Not by much, just a few milliseconds over 6 months, but still. Milliseconds count when you're dealing with clocks that throw shade at the idea of ever being wrong. Historians still argue whether the invention of the mechanical clock or the atomic clock had a greater impact on civilization. Mechanical clocks helped organize labor, agriculture, and religious rituals. But atomic time? It quietly underpins everything from internet infrastructure to financial markets. Even stock exchanges run on split-second accuracy. A delay of just a few microseconds can make or break $1 billion trade. And here's your fringe fact of the night. Some scientists are now experimenting with quantum clocks, so precise they could start challenging the very constants of nature. But we'll save that mind trip for later, when you're even sleepier. For now, just know that cesium doesn't lie. It vibrates at the same rate no matter what drama is unfolding on Earth. It doesn't care about deadlines, heartbreaks, or when the pizza delivery says, arriving in 10 minutes. It simply ticks, tick, 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 and you're floating above it all, watching as humanity learns to divide the infinite into bite-sized moments. You can see scientists calibrating equipment in a vacuum-sealed chamber. You can hear the whisper of microwave pulses nudging atoms back and forth between energy levels. You can almost smell the quiet sterility of the lab, a mix of cold metal, plastic gloves, and intellectual overachievement. But you also catch a glimpse of something stranger. A future where time isn't just measured, but manipulated. Where clocks might detect the subtle sway of gravity from underground rivers or earthquakes before they even strike. Where timekeeping becomes so refined that it starts poking holes in reality itself. You're not there yet. Right now, you're just letting the cesium sing. So next time you microwave your leftovers for 90 seconds, remember, you're using a form of time so precise it helps steer missiles, synchronize data centers, and map the stars. And all of it is built on atoms. Little vibrating reminders that time, no matter how abstract, always has something solid underneath it. You're walking through a garden, not the soft, mossy kind, but one made of shadows and sunlight, stone columns and carefully raked sand. There's no digital tick here, no atomic hum. Just the slow crawl of light across a stone surface, the kind that reminds you time used to be read by watching shadows. Welcome to the age of clocks before clocks. Before atoms were ever bullied into keeping perfect time, before springs and gears and digital screens, you had nothing but the sky, and some pretty clever humans trying to make sense of it. Imagine being a farmer in ancient Egypt, staring at the Nile and wondering when it might flood again. You'd notice that the star Sirius rises just before dawn, every 365 days, and with that knowledge, you might build your year. That's not superstition, that's proto-timekeeping. You're tracking the cosmos to tell you when to plant your crops and when to panic about your food supply. Sundials followed shortly after. A stick in the ground? Timepiece. That's the gnomon, by the way, not a Pokemon, but the upright part of a sundial that casts a shadow. The Babylonians and Greeks figured out how to etch circles and angles so they could read hours like chapters in a book. Of course, these early clocks had one fatal flaw: night. The sun would dip, the shadows would vanish, and your clock would quit its shift. No problem. Enter the water clock or clepsydra, literally water thief. Imagine a bowl with a tiny hole in the bottom, dripping steadily into another container marked with time increments. It's not accurate by modern standards, but it's quietly brilliant. You're now counting time in liquid. The ancient Chinese, Greeks and Egyptians all used water clocks in some form. In fact, the Greek engineer Ctesibius once designed a water clock so fancy it had gears, floats, and even a dial with moving hands. It was practically a smartwatch, minus Bluetooth and existential dread. Still, water clocks had their quirks. They'd speed up in summer heat, slow down when the water thickened, and completely break if a pigeon decided to take a bath in them. But that didn't stop them from becoming centerpieces in temples and public squares. These were monuments to the human need to know when to wake, when to pray, when to stop making soup. Now, not every civilization was obsessed with strict schedules. The Mayans, for instance, tracked time on a cosmic scale. Their long count calendar spanned roughly 5,000 years and was carved into stone with the confidence of people who fully intended their calendar to outlast empires. Historians still argue whether their famously misunderstood 2012 end date was a doomsday prophecy or just the Mayan version of out of pages flip to next calendar. Meanwhile, in India, elaborate shadow clocks were carved into stone temples, using precise angles and sunlight to track the passage of time. Many of these ancient instruments still work today, and some are accurate to within minutes. Not bad for stone and sunlight. Now drift over to medieval Europe, where mechanical clocks finally burst onto the scene around the 14th century. These weren't portable or even accurate, but they were loud. Bell towers rang out the hours in town centres, often more as a public spectacle than a precise measurement. It's sometime around now, the bells seem to say, give or take the blacksmith being late to wind the mechanism. The mechanical escapement, the little mechanism that allows gears to release at regular intervals, revolutionised everything. It made clocks more accurate, but more importantly, it made clocks count time instead of merely displaying it. Every tick and tock became a controlled fall, a miniature gravity-powered descent into the future. And then the humble hourglass. 2 bulbs of glass, some carefully sifted sand, and the mesmerising fall of time you can actually watch. These were used in navigation, kitchens, even sermons, because nothing says wrap it up like visible sand death. Fun fact, the sand in hourglasses was often dyed or ground finely to prevent clogging, kind of like artisanal pasta, but with more existential dread. Let's not forget the astronomical clocks either. By the 15th century, towns like Prague and Strasbourg unveiled towering mechanical wonders that didn't just show the hour. They tracked the moon phases, zodiac constellations, even planetary positions. These weren't just clocks, they were statements. Behold, they seemed to say, we have conquered the sky, with gears. Of course, that was a bit of an overstatement. Time was still a local thing. Noon in one village might be 5 minutes earlier than in the next. That wasn't a problem until trains came along and needed synchronised schedules, but we'll unpack that chaos a little later. Fringe fact for your brain to roll over as you drift deeper. In ancient Japan, temple clocks didn't divide the day into 24 equal hours. Instead, they split daylight and nighttime into 6 equal segments each, which meant hour lengths changed with the seasons. Yes, their hours were longer in summer and shorter in winter. These were called temporal hours, and they made perfect sense in a world ruled by sunlight rather than wristwatches. Try programming that into your smart calendar. So here you are, hovering through history as humans obsessively count drips, cast shadows, and grind gears just to understand the passage of time. You've seen kings rely on water bowls and monks listening for bells. You've watched sunbeams crawl across temple stones and sand spiral silently down the neck of an hourglass. And all of this effort was humanity's long winding way of asking the same question over and over. Is it time yet? You don't need to answer. Just listen to the quiet tick of invention behind you, echoing all the way from sundials to atom-splitting accuracy. Time, once wild and cosmic, is now something you can hold in your hand. Or at least, pour carefully into a glass bowl while you wait for the soup to finish. You're standing at the train station in 1905. The steam hisses softly, the whistle howls, and the hands on the station clock tick toward noon. You glance at your pocket watch, except it's already noon there too. Perfect sync. Or is it? Now zoom out. You're in one city, the train is headed to another. Whose noon is it really? Is there one universal now, or is that just something polite society agrees not to argue about over lunch? Cue Einstein walking into the room, likely with unbrushed hair and a theoretical axe to grind. Because if there's one person determined to ruin your day, or more accurately your wristwatch, it's Albert Einstein with his pesky theory of relativity. And yes, relativity absolutely ruins your watch. Until this point, you, along with most of human civilization, have happily assumed that time is absolute, that it flows the same for everyone, everywhere, like some celestial river running calmly past us all. A second is a second is a second, except it isn't. In 1905, Einstein drops his theory of special relativity, and suddenly, time is not a constant. Instead, it bends, it stretches, it squishes like a marshmallow when you change speed or move through gravity. Time becomes relative. Let's break this gently. According to Einstein, the faster you move, the slower time ticks for you, relative to someone at rest. This isn't sci-fi, it's physics, it's real, it's been measured. Imagine you're in a spaceship flying at near the speed of the light. You're chilling, sipping freeze-dried coffee, reading celebrity gossip from 2057. For you, only a few months pass, but back on Earth, years, maybe decades have rolled by. You return and your friends have aged, your favourite pizza place is a museum, and everyone communicates telepathically now. Thanks, relativity. This effect is called time dilation, and yes, it applies even in small doses. For example, atomic clocks flown around the Earth on commercial airliners do tick slightly slower than those left on the ground. It's a tiny difference, but it's measurable, real, and it means your watch isn't lying. It's just obeying the universe's weird rules, and that's just special relativity. Things get even messier when Einstein throws in general relativity in 1915. Now, not only does motion affect time, so does gravity. Here's the deal. Gravity doesn't just pull on objects, it warps space-time itself. Imagine space-time as a stretchy fabric. A heavy object like a planet or star causes a dip in the fabric. Time flows more slowly the closer you are to that massive object. The deeper the gravity well, the slower your time runs compared to someone in a shallower spot. That means time literally moves faster at the top of a mountain than it does at sea level. Not metaphorically, not feels like. Actually, provably faster. You age a few nanoseconds faster per year by simply living in a penthouse apartment. Take that gravity. This phenomenon, gravitational time dilation, has been confirmed with synchronized atomic clocks placed at different altitudes. The difference is minuscule, but real. If you're listening to this while hiking, congratulations. You're technically outpacing your couch-bound clone. Historians still argue whether the public truly understood the implications of Einstein's work during his lifetime. Sure, there were newspaper articles with equations and pictures of bent light beams, but most people still check their clocks assuming time was a universal constant. It wasn't until the 1970s, and the rise of GPS, that Einstein's theories went from mind-bending thought experiments to practical engineering necessities. Ah yes, GPS again. Those satellites you rely on to not end up in a lake. They orbit Earth at high speeds and altitudes, which means both special and general relativity are affecting their onboard clocks. If engineers didn't correct for these relativistic effects, GPS would accumulate an error of about 10 kilometers per day. So yeah, Einstein wasn't just being dramatic. And here's your quirky bedtime fact. In 1971, scientists flew 4 atomic clocks around the world on commercial planes, eastward and westward, and compared them to identical clocks that stayed put. The moving clocks experienced time differently, exactly as predicted by relativity. It was called the Haffel-Keating experiment, and it was like the universe saying, yes, Einstein's right, again. Of course, this all begs a sleepy, unsettling question. If time ticks differently for everyone depending on where they are and how fast they're moving, is there any such thing as a universal now? And the answer is, not really. There is no master clock in the sky counting time for everyone at once, no cosmic narrator tapping a stopwatch with your name on it. Instead, everyone moves through time at their own pace, subtly influenced by motion and mass like dancers following individual metronomes, which means two people in two different places, no matter how synchronized, are technically never experiencing the same now. They're just approximating it, sharing it imperfectly. Time, it turns out, is intensely personal. It's one of the reasons sci-fi stories about time travel get so delightfully messy. The more you understand relativity, the harder it is to write a plot where someone goes back to a fixed moment, as though time were a hallway with numbered doors. Because time isn't a hallway, it's more like a puddle, uneven, warped, and constantly sloshing around. So now you're floating above Earth, watching time bend and ripple like heat waves on pavement. You see astronauts in low Earth orbit aging slower than the people watching them on TV. You see mountain climbers wrinkling slightly faster than beach bums. You see satellites constantly adjusting their clocks to avoid GPS chaos. And somewhere, Einstein is smiling, probably late by everyone else's standards. So yeah, relativity ruins your watch. But in return, it gives you something better. The realization that time is flexible, responsive, and just a little bit sassy. It's not an invisible thread stretched across the universe. It's a dance, a distortion, a deeply personal experience. And yet, we still call it keeping time, as if it can be stored, guarded, or saved. Sorry, time doesn't want to be kept. It wants to bend. You're floating now, far beyond Earth, beyond stars, beyond anything your sleep-deprived brain would dare call familiar. There's no up, no down, no calendar. Just you and a number so tiny, so mind-numbingly small, it makes a nanosecond look like a lazy Sunday. This is Planck time, the shortest meaningful unit of time in the known universe. And by meaningful, I mean it's the tiniest slice of time we can talk about before physics gives up and throws the chalk at the blackboard. 1 unit of Planck time is approximately 5.39 times 10 to the negative 44th seconds. That's a decimal followed by 43 zeros and then a 5. It's so small you can't even count to it, not because you're bad at math, but because the act of counting takes longer than the unit itself. If the entire span of 1 second were stretched out across the entire Milky Way, Planck time would be smaller than a virus on a dust particle floating in a back alley 3 galaxies over. Probably being sneezed on. So, why do we care? Because Planck time represents the limit, a kind of basement of time. Below this threshold, our current understanding of physics breaks down. It's where quantum mechanics and general relativity stop playing nice. You're in a realm where even the idea of before and after gets fuzzy, and where space-time itself might not even be continuous. It might be pixelated, quantized, like reality is running on some kind of cosmic 8-bit processor. Think of it this way. If time were a movie, Planck time is the smallest possible frame. Anything shorter than this wouldn't just be unfilmable, it would be undefined. The universe doesn't seem to allow smaller ticks, and it's not just an arbitrary number. Planck time comes from combining 3 of the universe's fundamental constants: the speed of light, c, the gravitational constant, g, and Planck's constant, h bar. When you blend those 3 together in just the right way, you get this incredibly small unit that seems to whisper, "Here be dragons," or at least, "Here be questions." Because for all our equations and thought experiments, we still don't know exactly what happens at the Planck scale. Did time itself begin at the first Planck tick after the Big Bang? Did the universe have a 0 point? Or was there some unknowable haze of quantum foam bubbling before it all settled into the flow of time we now experience? Historians still argue whether early 21st century physicists were too cautious or too speculative in their hunt for a theory of everything, a single framework that merges quantum mechanics and general relativity into one cozy equation. That missing puzzle piece is crucial if we ever want to describe time beyond the Planck scale. String theory gives it a shot, so do loop quantum gravity and other more exotic frameworks. Some of these suggest that space-time is made of discrete units, that space, and therefore time, is chunky at the smallest levels, like Lego bricks, except more confusing and far less likely to be stepped on barefoot. And then there's the question of causality. Below the Planck timescale, does cause and effect even make sense? If two events happen closer together than 5.39 times 10 to the negative 44th seconds, can we really say one caused the other? Or are we just layering human logic onto something too weird for logic to handle? Here's a quirky little nugget to keep in your sleepy pocket. Some physicists suggest that Planck time might be related to the holographic principle, the idea that everything in our universe could be encoded on a two-dimensional surface somewhere, like a cosmic hard drive. If that's true, time itself might be an emergent property. Not something fundamental, but something that shows up only once the universe is big and boring enough. Don't worry, it's not your job to solve that. For now, just picture it. The first measurable tick of the universe. Before stars, before matter, before light, there's this threshold where time begins to make sense, like the first key struck on a piano in a previously silent room. That key? It's Planck time, and everything you've ever known from your birthday to your worst haircut happened billions upon billions of ticks after that, which, oddly enough, means you're very late to the party. There's a sort of poetry to it. The very foundation of time, as we understand it, is a number that is both unimaginably small and yet foundational to everything that came after. Planck time is like the first grain of sand on an eternal beach. You'll never see it, never touch it, never feel it, but every step you take depends on it being there. Let's zoom out a bit. If you tried to create a clock that ticked every Planck time, it would tick more than 10 to the 43rd power times per second. That's more than a trillion times, and no, your Apple Watch is not getting that firmware update anytime soon. So why doesn't time move in Planck-sized increments for us? Because we're enormous. To us, even nanoseconds are fleeting. Our brains, our biology, our machines are all built to process time in huge chunks by comparison. But deep down, under the skin of the universe, it may all be playing out in hyper-rapid, Planck-sized pulses. A jittery dance so fast and fine-grained that we only perceive the blur, not the beat. It's kind of like how a film appears smooth, even though it's made of individual frames flashing by. If time is a movie, Planck time is the frame rate. Only this movie is cosmic, eternal, and directed by, well, whoever programs the simulation, if we ever get around to believing in that. So now, as you drift somewhere between seconds and stardust, think of the ticking beneath everything. Not the slow tick of a grandfather clock, or even the precision of an atomic clock. Think smaller. Think tiny vibrations, too quick to name, too essential to ignore. And remember this, if time does have a minimum unit, then reality itself might be a song composed note by note in Planck-sized rhythm. A melody so fast you never hear the notes, only the music. Sleep well, little observer. The universe has been keeping time long before you showed up. You're standing in a quiet room that isn't a room. It's black, but not empty. Cold, but not lifeless. Around you, a faint glow pulses like distant embers, the dim afterglow of creation itself. You're face to face with the cosmic microwave background, or CMB, and though it's not a clock in the traditional sense, it just might be the universe's most ancient and reliable timekeeper. Let's rewind for a second. Well, several 100,000 years. The universe has just been born, in a fiery flash we like to call the Big Bang. For a while, everything is too hot, too dense, too chaotic for light to move freely. Photons, the tiny packets of light, are bouncing off electrons and protons like toddlers on a sugar high in a bouncy castle. Time is passing, yes, but there's no visibility, no signal, just a glowing fog. Then something incredible happens. About 380,000 years after the Big Bang, things cooled down just enough for the electrons to settle down and bond with protons, forming neutral hydrogen atoms. Suddenly, light is free to travel. The universe becomes transparent for the first time, and those newly liberated photons begin a journey that hasn't stopped. That glow? That's the CMB, ancient light stretched and cooled over billions of years by the expansion of the universe, now registering at a chilly 2.7 Kelvin, just barely above absolute zero. You can't see it with your eyes, but it's everywhere. It fills all of space, like the softest, oldest nightlight. And here's the part that makes you want to wrap yourself in a weighted blanket and say, "Wow," very softly. This glow carries time-encoded information. It's a record of the universe's earlier structure, a fossilized moment, a snapshot of the cosmos when it was just a cosmic infant with big plans. Now you're probably wondering, how exactly does this ghostly microwave fog help us measure time? Well, the CMB acts like a cosmic timestamp. It marks a very specific moment in the history of the universe, known as recombination, when atoms formed and light was unleashed. Anything that happened before this is basically invisible to traditional telescopes. It's the edge of the observable universe, not in space, but in time. Cosmologists use the temperature variations in the CMB, those tiny fluctuations like freckles on the face of the sky, to understand how matter was distributed back then. And from that, we can estimate how long the universe has been expanding. That's how we got the now famous age, about 13.8 billion years. Of course, that number is still debated. Some recent measurements suggest the universe might be slightly younger or older, depending on which method you trust. So yes, even with all this high-tech data, the universe is still lying about its age like it's trying to get into an R-rated movie. Historians still argue whether the discovery of the CMB in 1964 by Penzias and Wilson was truly accidental. The story goes that they were working with a radio antenna and kept picking up a weird background hum. They tried everything, clearing bird poop out of the equipment. Yes, really, checking every component, until they realized they were hearing the universe's afterglow. It wasn't a flaw. It was the beginning of cosmic archaeology. Since then, satellites like COBE, WMAP, and Planck, no relation to Planck time but still a physics darling, have mapped the CMB in exquisite detail. These missions have shown us that the early universe wasn't perfectly smooth. There were tiny, tiny temperature differences, fractions of a degree, that eventually led to the formation of galaxies, stars, and planets. You know, all the good stuff. And the beauty of it is this. Those tiny ripples are still rippling. They've expanded, cooled, and shifted, but their pattern tells us when they started. It's like finding an ancient musical score written in the vibration of the air, still playing billions of years later. Now for a quirky little detour, ever hear of the axis of evil? No, not the political phrase, the one in cosmology. It's a strange anomaly in the CMB. Some data suggest that the temperature fluctuations in the background radiation may be aligned in a way that defies the expected randomness. That's deeply weird and deeply controversial. Some scientists think it's just a statistical fluke. Others think it hints at new physics. Fringe, yes. Fun, absolutely. And here's something cozier to think about. About 1% of the static you hear on an untuned TV or radio, that's the CMB. Every time your old television sputtered that grey and white snow, you were literally hearing the afterglow of the Big Bang. That's cosmic static. Ancient light turned into hiss. So what does this have to do with timekeeping? Everything. The CMB is the earliest universal reference point we have. It's how we anchor cosmic events, how we calibrate our timelines. Every galaxy we observe, every supernova, every black hole, we place them on the cosmic timeline using the CMB as our origin marker. It's not just background noise, it's the backdrop. Even as the universe expands and cools, the CMB remains. It's dimming, sure, redshifting into ever longer wavelengths. But for now, It's a perfectly uniform curtain stretching across the sky, a clock face without hands ticking in the language of radiation. Some scientists speculate that billions of years from now, the CMB will become undetectable. The universe will be so stretched and cold that this ancient glow will fade completely out of view. Future civilizations, if they exist, may never know it was there. Without it, they might not even be able to tell how old the universe is. So here you are, standing quietly in this cosmic glow, knowing something future beings might never see. You're gazing at the first light, stretched across time and space like a soft, warm quilt stitched with galaxies. It doesn't tick like a watch, it doesn't buzz like a smartphone, but it keeps time perfectly, softly, endlessly. You're walking down an imaginary street now, but the buildings are all clocks. One with Roman numerals ticks dramatically, another hums softly in binary, a third is just a big sun carved into a wall. But tucked between them all, awkward and very human, is a booth with a flashing neon sign that says, "Time zones are made up in bold, blinking letters." And yeah, they kind of are. Let's face it, time is weird enough on a cosmic scale, but humans have somehow made it even messier down here on Earth. You've built imaginary boundaries that slice the globe like a giant orange, and decided that based on where you're standing it might be 3 p.m. or tomorrow. Welcome to the glorious chaos of time zones. Now it all kind of started with good intentions. In the beginning there was the sun, simple enough. Noon was when the sun hit its highest point in the sky. Every town, city and goat path worked off its own local solar time. The problem? As civilization advanced, and more importantly as railroads happened, this system became a logistical nightmare. You can't run a train network if every town is 17 minutes off from the next. Imagine trying to coordinate a cross-country train ride in the 1800s, only to discover your ticket says 3:15 in your town, but 3:05 in the next, and 2:53 in the one after that. You'd miss your connection, your lunch, and possibly your will to live. So, in 1884, the International Meridian Conference was called. A bunch of delegates from around the world gathered, probably wearing monocles and looking slightly sweaty, to divide the Earth into 24 standard time zones, each roughly 15 degrees of longitude apart. The prime meridian was placed in Greenwich, England, and the system we mostly use today was born. But, and here's the good part, it didn't stay neat. Because while the Earth spins with robotic precision, humans do not. Countries and regions started bending the rules, nudging their clocks to better match daylight, politics, or just personal preference. Some places sit comfortably within their assigned time zone. Others, total chaos. Take India, for example. It's 5.5 hours ahead of UTC, Coordinated Universal Time. Why the half hour? Because they said so. Then there's Nepal, which just had to one-up India by being 5 hours and 45 minutes ahead of UTC. Not 6 hours, not 5.5, 5:45. It's the horological equivalent of a passive-aggressive text. Australia, a glorious patchwork. The state of South Australia is 9.5 hours ahead, while the East Coast is 10. Some regions follow daylight saving time, others refuse. And then there's Lord Howe Island, which, not to be outdone, is UTC plus 10:30 normally, and UTC plus 11:00 during daylight saving. That's right, 30-minute daylight saving. Historians still argue whether daylight saving time has ever actually saved anything except for causing missed meetings and microwave clock confusion. It was introduced in various countries during wartime to conserve fuel, but in the modern age, its usefulness is debatable. Some say it improves productivity, others argue it ruins sleep cycles and increases heart attacks. And let's be honest, you've probably forgotten to change your oven clock more than once. Fringe fact to sleep on, there's a town in North Korea, Pyongyang, that used to run on Pyongyang time, a unique time zone 8.5 hours ahead of UTC, just to be different from South Korea. They later resynced with the South as a gesture of unity. So yes, time zones can be political gestures. Imagine weaponizing a wristwatch. And what about the international date line? That invisible zigzag out in the Pacific where the date suddenly jumps forward or back depending on which way you're flying. It's not a straight line. It bends around islands like it's drunk. Cross it from west to east and you go back in time by a day. Cross it the other way and boom, it's tomorrow. This leads to surreal scenarios like the one involving Samoa. In 2011, Samoa literally skipped an entire day, December 30th, to move itself to the other side of the date line and align better with Australia and New Zealand for business. One day it was Thursday, and then, just kidding, it was Saturday. So if you're keeping score, time zones are technically rooted in astronomy, but in practice they're built on human compromise, political statements, and a sprinkle of stubbornness. And yet, for all the chaos, the system mostly works. Planes take off and land. Global stock markets open and close. Birthday wishes get sent across hemispheres with only a few hiccups. It's a system held together with duct tape, diplomacy, and digital syncing. Even your phone, yes, the very device you're using to read or listen to this, has to constantly check in with servers around the globe just to keep your local time accurate. It doesn't just know, it checks, it cross-references. It asks, are we still pretending it's 3 p.m. in Ohio? Okay, great. Now zoom out. You're in orbit, looking down at Earth. You see an invisible grid superimposed over the planet, lines of longitude snapping into time zones, bending around countries, slicing across oceans. You see 7 a.m. blooming across Asia, rolling westward like a wave of alarms and coffee pots. You see 5 p.m. landing in Paris, just as dinner starts sizzling. Midnight drops like a curtain across the Pacific, erasing today for some and starting it fresh for others. And above it all, satellites, quietly tracking universal time, ignoring time zones entirely. Because in the world of precision timekeeping, things like local time are irrelevant. The Earth doesn't care what we call it, it just spins. But humans, we care deeply. We name hours, we argue over daylight savings, we draw jagged lines through forests and deserts just to say, time changes here. Because time in the human world is part math, part convenience, and part sheer cultural stubbornness. So next time you're jet-lagged or trying to schedule a Zoom meeting with someone in Auckland, just remember, time zones are entirely made up, and everyone involved is just doing their best. Also, somewhere on Earth, it's always happy hour. You're floating now, not in space, but somewhere stranger, somewhere quieter. You're surrounded by ticking clocks, grandfather clocks, atomic clocks, hourglasses, dripping faucets, and they're all ticking in perfect unison, until they don't, until one stops, another reverses, one just hums like it's forgotten what time even is. And in the middle of this quiet, surreal museum of motion and stillness, a question hangs in the air like fog. Does the universe even care about time? It sounds like a setup for a deep podcast episode, or the opening line of a philosophy professor's midlife crisis. But it's a real, serious question in modern physics, and no, there isn't a simple answer. Because when you zoom out far enough, time starts to look suspiciously like something we invented. Or at least, something weirder than we've been led to believe. Start with the basics. In Newton's universe, time is an absolute river, always flowing, always forward. Every event happens on a single universal clock, whether you're on Earth or Jupiter or doing cartwheels near a black hole. Time was a dependable background track, ticking evenly like a metronome, regardless of what the instruments are doing. Then Einstein broke that model, as we saw earlier, and showed that time bends with motion and mass. Okay, fine, flexible time. We can live with that. But modern physics takes it a step further and asks, what if time isn't even fundamental? What if it's just an emergent property, something that only exists because we exist? Breathe that in for a second. What if the universe itself doesn't feel time? What if it's just there? Some interpretations of quantum mechanics suggest just that. In these models, the most basic equations of the universe, things like the Schrödinger equation, the mathematical heart of quantum theory, don't include time at all. They describe probabilities, relationships, interactions, but they're timeless, static, like a painting, not a movie. To be clear, you experience time. Every tick of your pulse, every cramp in your back, every cup of tea that slowly cools. But those sensations might not be telling you how the universe works. They might just be telling you how your brain works. Historians still argue whether time has always been treated as a primary axis in our understanding of the cosmos, or whether we simply needed it as a mental crutch, something to hold on to while everything else spins. Let's take a detour to the block universe theory. According to this idea, all of time, past, present, future, exists simultaneously. Picture it like a loaf of bread. Each slice is a moment in time. You, with your limited perspective, can only see one slice at a time, experiencing the illusion of movement from one slice to the next. But the loaf? It's already there. The entire thing. Nothing is happening. It's just being. And if that's true, then the universe doesn't care about time. It doesn't do time. It just is. Now here's the kicker. This idea isn't just philosophical fluff. It shows up in real physics. Einstein himself once wrote that the distinction between past, present, and future is only a stubbornly persistent illusion, which is the kind of thing you write when you're both brilliant and slightly out to lunch. So then what is time? Well, one camp argues it's purely relational. That is, time only exists because things change. Clocks tick, planets spin, eggs fry. Without change, there's no time. If you took a snapshot of the entire universe at one moment, and there was no motion, no heat, no change, then time wouldn't mean anything. You could stare at that snapshot forever, and it would never become a sequence. On the other hand, some scientists argue the opposite. Time is real, and change is the illusion. That underneath the illusion of motion, there's a deeper, static structure to reality. You're not moving through time. You're just scanning through a series of frozen moments, like a flip book, except no one's flipping it. You just think they are. If your head is spinning, good. Time would be proud. Now let's take a sleepy little walk into thermodynamics. We've talked about the arrow of time, that idea that entropy always increases, and that this increase is what makes time feel like it moves forward. Hot things cool, broken plates don't unbreak, your favourite series ends and you can never watch it for the first time again. But entropy isn't a law of nature like gravity. It's statistical. Most systems tend toward disorder, sure, but not all. In theory, nothing prevents time from reversing. The equations of physics work just fine going forward or backward. The laws don't care, we do. Which brings us back to the universe. Does it care about forward and backward? About before and after? Probably not. There's even an idea floating around out there called the timeless universe hypothesis. In this model, time is a trick of human perception. You experience one moment after another because your brain is wired to store memories in a specific order. Your consciousness creates time by stitching those memories into a linear narrative. It's like a dream where you assume there's a plot, but there isn't. Just moments and the illusion of motion. And the weirdest part? Some physicists don't just entertain this possibility, they kind of prefer it, because it makes the math cleaner. But before we start uninstalling all our clocks and just vibing forever, it's important to remember that this isn't settled science, not even close. In fact, many researchers are still pushing hard to figure out whether time is fundamental or emergent, whether it's a building block or a side effect. The debate is ongoing, and it's one of the biggest questions in physics. Is time something the universe creates, or something we project onto the universe like a movie projector, casting light onto a blank wall? The answer could change everything. Not just how we build equations, but how we think about memory, identity, cause and effect, even death. But for now, you're here, in a world where time still seems to move forward, where your tea still gets cold, where you still need to set an alarm. Even if the universe doesn't care about time, you do. Because time is the thread that stitches your story together, one scene at a time. Whether it's real, emergent, or just a very convincing hallucination, it still gives shape to your life. And honestly, that's enough for tonight. You're lying flat now, eyes closed, breath steady, when something gently tugs at the back of your mind. Not the tick of a clock, not the buzz of a phone, but the quiet, relentless hum of the universe doing what it does best, falling apart. This sleepy friend is entropy, the one-way street of time, the reason ice melts but doesn't unmelt, the reason your neatly organised sock drawer inevitably devolves into a chaotic sock salad. Entropy isn't just a nuisance, it's the cosmic arrow of time, but let's tiptoe into it gently. In its simplest form, entropy is a measure of disorder, or more precisely, it's the number of ways a system can be arranged while still looking the same from a certain perspective. Think of a deck of cards. A fresh, crisp deck, sorted by suit and number, is low in entropy. The second you shuffle it, entropy spikes. The number of possible combinations has exploded, and once you start dealing hands, well, chaos reigns. This idea isn't just about card games or lost socks, it's about everything. From the early universe to the end of time, entropy shapes the direction of events. Why? Because statistically speaking, disorder is more likely than order. There are more ways for things to fall apart than to stay neat. More ways for heat to spread than to concentrate. More ways for your spaghetti leftovers to congeal into a tragic cold lump than to reassemble into hot pasta. The second law of thermodynamics, arguably the most depressing law in all of physics, says that in a closed system, entropy either stays the same or increases, never decreases. That's why time feels like it only flows one way. Because things move from ordered to disordered, from ice cubes to puddles, from stars to ash, from your 20s to your 30s, when suddenly your knees make that noise. Historians still argue whether ancient thinkers like Heraclitus, who famously said, "You can't step in the same river twice," were hinting at this idea of irreversible change. They didn't have the math, but they certainly had the vibe. And the arrow of time isn't just philosophical, it's practical. Imagine you record a video of cream being stirred into coffee. Watch it forward, and it makes perfect sense. But play it backward, and your brain rebels. That's not how cream unmixes. That's not how time works. But here's the mind-bending part. The laws of physics don't actually care. Most fundamental equations work perfectly in either direction. Newton's laws, reversible. Schrödinger's equation, reversible. Even gravity, electromagnetism, they don't prefer forward over backward. So what gives? Why do we experience time as a one-way flow when the universe's rules don't enforce that? The leading culprit, once again, is entropy. While individual particles can reverse course without a fuss, large systems, like your body or the entire universe, have so many moving parts that reversing all of them is statistically impossible. It's not forbidden, just so unlikely it might as well be. That's why a glass can fall off the table and shatter, but never let back up and reassemble. It's not that it couldn't, in theory. It's that the number of microscopic steps required to undo the damage is astronomically huge. The entropy increase from the shattering is so much more probable than the decrease required to reverse it. So entropy becomes time's compass, the quiet whisper that tells you forward. It's not loud, but it's firm, and it's everywhere. Here's a fringe fact for your pillow. Black holes have entropy too. In fact, according to physicist Jacob Bekenstein and later expanded by Stephen Hawking, the surface area of a black hole's event horizon is directly related to its entropy. That's right. The boundary of a black hole can be measured in terms of how much information it hides. This idea helped bridge quantum mechanics and general relativity, and it led to the insight that black holes aren't truly black. They radiate tiny amounts of heat and slowly evaporate over time. Even the darkest places in the universe can't escape entropy. Now stretch your imagination just a little further. Entropy not only gives time a direction, it may also determine the structure of time. Some scientists have proposed that time is born out of entropy itself, that without entropy, time might not even exist in a meaningful way. In a completely static, zero-entropy universe, Would there be any change to measure, any before or after? The answer seems to be no. Without change, there is no time, no clocks, no cause and effect, just an eternal, unblinking now. Not the peaceful kind, the existential horror kind. But entropy, bless its messy heart, keeps everything moving. And speaking of mess, let's talk about your room, your kitchen, your inbox. These are entropy playgrounds. You clean them, organize them, bring them into a low entropy state, and within hours, entropy strikes. Dishes reappear in the sink, dust settles, your laundry multiplies like rabbits with a grudge. But here's the twist. To clean your room, you have to use energy, burn calories, move things. You're not reducing entropy overall, you're just shuffling it around. Lowering entropy in one place increases it elsewhere. The total balance stays in the universe's favour. And this is true even of life itself. Your body maintains order, homeostasis, by constantly burning energy and generating waste. You're like a tiny entropy-fighting machine that survives by outsourcing mess to the rest of the universe. Neat. Yet for all its inevitability, entropy doesn't mean everything is doomed. It just means that change is constant, that perfection is temporary, that time moves toward complexity, toward mixing, toward heat death. Yes, we said it. Heat death. The far, far future of the universe when everything has spread out, cooled down and hit maximum entropy. No gradients left to exploit, no work left to do. Just a cosmic room temperature sigh. We'll talk about it more later, but it's a place where time might lose all meaning. A flat line on the cosmic heart monitor. But tonight, you're not there. You're still in the messy middle. You still have change. You still have clocks and candles and that one drawer you pretend doesn't exist. And you still have time, thanks to entropy. You're standing at the edge of something dark, colder than cold, denser than dense, and more mysterious than your unread email folder. Ahead of you, a black hole. Not the kind that swallows your schedule, but the real thing. A warped knot in space and time so intense it eats everything, including light. And yes, even time itself begins to misbehave in here. If you've been asking yourself, where does time really go wrong? Congratulations, you've arrived. Let's step quietly into the world of timeless places. Black holes are often described as collapsed stars with gravity so strong that nothing, not even light, can escape once it passes a boundary called the event horizon. But what they don't always tell you is what black holes do to time. Spoiler, they stretch it like taffy. According to general relativity, the closer you get to a black hole, the more intense gravity becomes, and the more intense gravity is, the slower time moves. This isn't metaphorical or poetic, it's literally measurable. Time slows down near strong gravitational fields. It's called gravitational time dilation, and near a black hole, it reaches its dramatic peak. From your comfy perch far away, you'd watch someone falling into a black hole slow down, and down, and down, until, at the edge of the event horizon, they'd seem to freeze in place forever, trapped in slow motion. But to the falling person, their clock ticks along just fine. They feel nothing unusual, no slowing. They fall, and then, presumably, get very, very squished. This idea was popularized in movies like Interstellar, where 1 hour on a planet near a supermassive black hole equals 7 Earth years. That's not just a plot twist, it's physics. Time bends, slows, and warps dramatically near black holes. If you really want to age slower, and don't mind being turned into a spaghetti noodle by tidal forces, this is technically your best option. Historians still argue whether our modern fascination with black holes began with Einstein's equations or with John Michell, an English natural philosopher who first proposed the idea of dark stars back in 1783. That's right. This concept is older than electricity in most houses, but Einstein's general relativity gave it teeth. In 1915, his theory predicted that if enough mass were packed into a small enough space, It would warp space-time so completely that a black hole would form. Enter Schwarzschild radius, the mathematical point of no return, the invisible boundary where time stops for an outside observer, light can't escape, and all paths lead inward. Once you pass this threshold, you're not just doomed in space, you're doomed in time. Inside the event horizon, space and time switch roles. You no longer fall through space, you fall through time, inevitably moving forward toward a singularity, a point of infinite density where the known laws of physics dissolve like sugar in tea. And yes, that part remains theoretical, because we can't observe a singularity, we can't even properly define it. Some physicists think the singularity is a mathematical bug, others believe it's real, a literal point where the universe says, here's where the rules break. But what we do know is this: black holes mess with time more than anything else in the universe. They represent the ultimate boundary, the final boss of timekeeping. Not because they destroy time, but because they make it meaningless, at least as we understand it. And here's your quirky bedtime bonus. Black holes evaporate, slowly, quietly. Via something called Hawking radiation, they leak energy and lose mass over trillions of years. A black hole the size of the Sun would take about 10 to the 67th power years to evaporate, long after stars, galaxies, and maybe even atoms are gone. What's leaking out isn't just heat, it's information, or at least we hope it is. Because for decades, physicists debated the black hole information paradox. If information falls into a black hole and is lost forever, that breaks the rules of quantum mechanics, which insists that information is never truly destroyed. So, is it gone? Or somehow preserved on the event horizon, encoded in the Hawking radiation, saved on a cosmic USB stick? We still don't fully know. But recent theories suggest that information isn't lost. It's smeared across the edge of the black hole like a weird, two-dimensional hologram. And if that's true, then the surface of a black hole remembers everything it's consumed, like the universe's grumpiest librarian. This brings us to an unsettling but poetic idea. Black holes may be the graveyards of time, places where past, present, and future collapse into a single unknowable moment, where events are so contorted by gravity that time ceases to behave like time. It becomes tangled, looped, frozen, a place where clocks are meaningless, and yet they might also be the keepers of time, trapping it, recording it, preserving its secrets just beyond our reach. You might be wondering what it's like to fall into one. Don't worry, you're not alone. Scientists have thought long and hard about it. There's even a term for the way you'd be stretched by the gravity gradient as you fall: spaghettification. Sounds delicious, feels horrifying. Your feet would experience more gravitational pull than your head, or vice versa, depending on how you fall, and you'd be pulled into a long, thin noodle of atoms. But before that, your experience of time would still feel normal. That's the eerie part. You'd never notice time slowing. Only the observers outside would see you pause, suspended forever on the edge. A cosmic ghost trapped in time. So now, as you drift back from the event horizon, you leave behind a place where time collapses, stalls, and eventually leaks away. And you're reminded, again, that time isn't a rigid thing. It bends, it flows, and sometimes it just stops returning your texts. Black holes may be the end of many things: light, matter, causality. But they're also the final test of time, a place where the ticking stops, where space gets stretched and time becomes a question, not an answer. And honestly, that's enough deep space dread for one night. You're floating again, but this time closer to home. Blue oceans curve beneath you, white clouds spiral gently above continents, and the whole planet turns silently, obediently. Somewhere down there, someone is brushing their teeth. Someone else is filing taxes. But right now, you're focused on a small silver capsule orbiting hundreds of kilometers above Earth. Inside it, a handful of astronauts sleeping, working, floating in microgravity, and aging just a little slower than the rest of us. Yes, you heard that right. You age slower on the International Space Station. Not by much, just a smidge of time shaved off here and there, but it's real and measurable and absolutely one of the weirdest gifts that Einstein ever left us. Let's unpack that with a sleepy shrug of curiosity. The International Space Station, or ISS, orbits Earth at a blistering 28,000 kilometers per hour, about 17,500 miles per hour. It's fast enough to circle the planet every 90 minutes, which means astronauts aboard the station see 16 sunrises and 16 sunsets every Earth day. While that's a scheduling nightmare for your circadian rhythm, it's heaven for physics experiments. And here's where time plays its trick. As we talked about earlier, Einstein's theory of special relativity tells us that the faster you move, the more time slows down for you compared to someone at rest. That effect, called time dilation, becomes noticeable when you're travelling at high speeds, like orbital speeds. Meanwhile, general relativity says that gravity also affects time. Stronger gravity means slower time. So in low Earth orbit, you're farther from Earth's surface, meaning gravity is weaker up there than down here. That actually speeds up time slightly. So now you've got two competing forces. 1, speed, slows time down. 2, lower gravity, speeds time up. Which wins? For the ISS, special relativity wins. The speed-induced time dilation is slightly stronger than the gravitational boost. So astronauts up there are indeed aging slower than us ground huggers by about 0.007 seconds per 6-month mission. 7 milliseconds. That's it. But don't laugh. This isn't just academic. We've measured it. Let's talk about the Kelly twins. In 2015, astronaut Scott Kelly spent nearly a full year aboard the ISS, while his identical twin, Mark Kelly, remained Earthbound. NASA saw an opportunity to study the biological effects of space by comparing two genetically identical people in different environments. The headlines, of course, loved the drama. Scott Kelly returns younger than his twin. While technically true, the time difference due to relativity was just 5 milliseconds. Not exactly a time travel plot twist, but it was real, documented, confirmed by atomic clocks. Historians still argue whether the twin paradox, this famous thought experiment about one twin aging slower due to high-speed travel, was ever meant to be literal. But in Scott and Mark's case, it became real-world data. Now this brings us to a deeper thought. Time isn't the same everywhere, even on your own body. Think about it. Your head is slightly farther from the Earth's centre than your feet. That means your head experiences slightly less gravity, so it ages a little faster. Not enough to throw a party for, but yes, technically your brain is always slightly older than your toes. If you lie down flat right now, you're equalising your personal time field. Congratulations, you've achieved peak relativity chill. And this effect is so precise that the world's most accurate atomic clocks can detect it even when moved by just a few centimetres. You raise a clock by a metre, it ticks faster. Lower it, it ticks slower. That's not science fiction, it's experimental fact. Now back to space. Astronauts on long-duration missions not only experience time differently, they also perceive it differently. In microgravity, their circadian rhythms get thrown out of sync. Light and dark cycles blur. Tasks take longer. Their sense of how much time has passed becomes warped. Some astronauts report that time seems to pass more slowly in orbit. Others feel the opposite. Either way, their experience of time is altered, not just physically, but mentally. And here's your quirky, slightly dreamy fact of the evening. Astronauts often dream of Earth. Not just in the poetic sense, they literally have vivid dreams about standing on solid ground, hearing bird song, walking in forests. It's a kind of time travel in the most human sense, a longing for normal time, gravity time, ground time. Meanwhile, back on Earth, satellites orbiting even farther out have to correct their internal clocks every single day to compensate for these relativistic effects. GPS satellites in particular are programmed to run slightly slow, so that once time dilation kicks in from their altitude and velocity, They sync perfectly with clocks on Earth's surface. If we didn't do that, your GPS location would be off by several kilometers within minutes. Relativity isn't just something cool to read about when you're too tired to blink. It's baked into your daily life. Every time you open your Maps app or call someone across the planet or watch a satellite weather update, you're interacting with systems that must account for time dilation or they break. That's the reality of modern timekeeping. It's no longer enough to have one standard clock. We now have to account for many clocks, each slightly out of sync with the others depending on motion, gravity, and altitude. It's a bit like trying to conduct an orchestra where every musician is sitting in a different gravity well. The only way it works is by knowing exactly how out of sync everyone should be, and correcting for it. So now picture it again. A small capsule silently orbiting Earth, astronauts floating through the day, their hearts beating, their watches ticking, their cells aging just a little more slowly. Not much, but enough. And here you are, back on Earth, moving through time like normal, but maybe with a bit more appreciation for how relative that normal really is. Time is not a fixed river, it's a shifting current, changing ever so slightly depending on where you stand and how fast you're going. And if you ever make it into space, even just for a little while, you'll come back younger. Now you're stumbling through the past, bleary-eyed and bewildered, holding a calendar that refuses to make sense. 1 month's too long. The next one's got 31 days for no good reason. February looks like someone gave up halfway through and just walked off the job. Congratulations. You've entered the chaotic realm of calendars. If timekeeping is humanity's love letter to order, calendars are the messy handwriting in the margins, crossed out holidays, double-booked Wednesdays, and a wildly inconsistent number of days that somehow got us all to agree on when to have birthdays. Let's roll back the stone wheels of history and take a slow, sleepy walk through the chronometric museum of Mayans, Romans, and a pope who, quite frankly, just wanted Easter to stop drifting. Start with the Mayan calendar, which was so eerily accurate it still spooks people today. The Mayans had multiple interlocking calendars, but the most famous is the long count, which tracked cosmic cycles over 5,125 years. That's not a typo. They made a calendar that stretched over 5 millennia, carved into stone, with the quiet confidence of people who knew they'd be misunderstood by 21st century internet theorists. And yes, 2012 came and went without the world ending, despite the memes. Historians still argue whether the end of the long count calendar was meant to signal apocalypse, or just a new cycle, like reaching December 31st and turning the page. You didn't panic when your 2023 wall calendar ended, did you? Then there's the Roman calendar, a hot mess that only became more confusing the longer it stayed in use. The earliest Roman system was a 10-month calendar, beginning in March. Yes, that's why September, October, November, and December literally mean 7th, 8th, 9th, and 10th months, but are now the 9th, 10th, 11th, and 12th. Language didn't update its software. Eventually they added January and February, but not in a very structured way. Days were often added or removed by officials for political reasons. In fact, the calendar could be, and often was, manipulated to extend a magistrate's term or delay an inconvenient election. If you think daylight saving time is annoying, imagine living in a world where months were regularly shuffled like a deck of cards. Enter Julius Caesar in 46 BCE, wielding a laurel crown and a strong dislike for calendar drift. He introduced the Julian calendar, which was based on a 365.25-day year. To keep things in sync with the solar year, Caesar added a leap day every 4 years. Simple enough, right? Except that 0.25 was actually a little too generous. The solar year isn't 365.25 days, it's more like 365.2422. So over time, the Julian calendar drifted. By the 1500s, the spring equinox, crucial for calculating Easter, was about 10 days off. The Pope was not amused. So in 1582, Pope Gregory XIII introduced the Gregorian calendar, which we still use today. He did what any frustrated scheduler would do. he deleted 10 days. Just gone. In Catholic Europe, October 4th, 1582, was immediately followed by October 15th. People went to bed and woke up over a week later. You didn't miss anything, unless you had a birthday or rent due in that window. Sorry. To avoid the same slow drift in the future, the Gregorian reform fine-tuned the leap year rule. A leap year happens every 4 years, unless it's divisible by 100, unless again it's divisible by 400. So the year 1600, leap year, 1700, 1800, 1900. Nope. 2000? Yes, again. It's like a math riddle designed to keep everyone slightly confused but mostly accurate. And even this new, improved system didn't roll out smoothly. Protestant and Orthodox countries weren't thrilled about a papal decree, so they stuck with the Julian calendar for decades, or even centuries longer. Britain didn't switch until 1752, and when they did, they had to delete 11 days to catch up. Public outrage followed. There were possibly exaggerated accounts of riots where people shouted, "Give us back our 11 days." Whether those riots actually happened is debated, but it's safe to say nobody likes waking up to find out half the month got yeeted. Russia held out even longer, finally adopting the Gregorian calendar after the 1917 revolution. That's why the October Revolution actually happened in November, depending on which calendar you're using. Just another friendly reminder that history and time are full of fine print. Let's not forget weirder attempts at calendar reform. The French Revolution brought with it the French Republican calendar, which had 12 months of 30 days, with 3 weeks of 10 days each. It was meant to free citizens from the tyranny of religious and royal influences, but it didn't last. People hated the 10-day work week, and the months, named things like Brumaire and Thermidor, didn't catch on. By 1806, Napoleon buried the experiment, and everyone happily went back to regular months, irregular days, and only slightly fewer revolts. And here's a delightful fringe fact to wind down with. In 1930, the Soviet Union tried its own calendar reform. They introduced a 5-day work week where each worker was assigned a colour group, and only people in the same colour group shared days off. This was supposed to increase productivity and eliminate religious observance. Instead, it destroyed family life, exhausted workers, and was wildly unpopular. It was scrapped within a few years, and we quietly agreed never to speak of it again. Today, our Gregorian calendar limps along, patched with leap years, daylight saving time, and awkward month lengths. It's not perfect, it's not even logical, but it mostly works. And every time you glance at your phone or check the date or schedule a meeting 3 Thursdays from now, you're participating in a deeply human, wildly imperfect attempt to pin down the flow of time, to name it, to hold it still, to give structure to the unstoppable. So when you stare at February and wonder why it only has 28 days, remember, it's not broken, it's just Roman. You're standing on a rocky plain now watching the horizon tint itself a gentle coral pink. The sky's thinner here, the ground dustier, the gravity a lazy whisper compared to Earth's constant pull. You're on Mars, and something's off. The sun is setting, but not in a fiery orange blaze like at home. It's a soft, dusty blue. Welcome to a planet where even timekeeping has to be reinvented. Because here's the cosmic punchline. Your Earth-based wristwatch is now wrong. Not by much, but enough to cause scheduling nightmares for every space mission planner trying to run 2 planets worth of clocks. You've landed in the strange world of Martian time, where the days are longer, the years are weirder, and nobody's quite sure what Monday means anymore. Let's start with the basics. A day on Mars, called a sol, is about 24 hours, 39 minutes, and 35 seconds. So close to an Earth day, and yet so inconvenient. That little extra bit might seem harmless, but for mission control teams running rovers like Curiosity or Perseverance, it adds up fast. Back on Earth, Sol 1 on Mars begins at a certain time, synced with the local Martian sunrise. But because each sol is about 39 minutes longer, Martian time gradually drifts away from Earth time. After a few weeks, mission planners are waking up in the middle of the night, working in bleary-eyed shifts that roll forward nearly an hour each day. It's like jet lag. That never ends. To cope, NASA engineers built special Mars watches. These modified timepieces tick slightly slower, matching the Martian soul. Some team members even changed the clocks on their phones and microwaves just to stay in sync during rover missions. And yes, they celebrated Martian holidays and Martian work weeks, which lasted just as long, only shifted off Earth time like a schedule that's perpetually sideways. Historians still argue whether our current Earth-centric timekeeping can ever truly scale to interplanetary life. As we inch closer to crewed Mars missions and maybe even settlements, the question looms: how do you schedule a society on another planet? A few things to consider. 1. A Martian year is about 687 Earth days, nearly twice as long. So your birthday? It's now every 22 months. Sorry. 2. Martian seasons also last longer and are more lopsided because of Mars's elliptical orbit. Winter in the northern hemisphere is short and chilly. Summer is long and weirdly mild. Good luck figuring out when to launch fireworks. 3. The Martian week? That's up for debate. Some have proposed keeping the 7-day Earth week for convenience. Others argue that a new society needs new rhythms. Now imagine being a future colonist. You wake up in a habitat built on a red plain, step outside in your suit and check your watch. But are you checking Earth time, Martian coordinated time, local base time? What about your friend in a dome 2 time zones away? Suddenly the logistical headache of timekeeping becomes very real. To solve this, scientists have proposed creating a new Martian Standard Time, MST, like Earth's Coordinated Universal Time, UTC, but slower. However, without global infrastructure, satellites, atomic clocks, synchronized systems, it's hard to define time across a whole planet with no cities. For now, NASA missions use Local Mean Solar Time, LMST, for the rover's landing site. It's a solar-based time specific to that exact longitude, so Curiosity runs on Gale Crater Time, Perseverance runs on Jezero Crater Time, and no, they're not the same. And here's your quirky tidbit: Mars has time zones too. In theory, if you divide its 360 degrees of longitude by 24 hours, like Earth, you get 24 Martian time zones, but with no government, no standard infrastructure, and no Starbucks to open at 7 AM. These time zones are more theory than practice. Even funnier, the Martian clock has already appeared in sci-fi. In Kim Stanley Robinson's Mars trilogy, settlers use a 24-hour clock stretched with a leap second at midnight. You get an extra tick each day. Not much, but it's like a sigh at the end of the day. A quiet acknowledgement that yes, you're not on Earth anymore. And speaking of which, Earth still matters. For early colonists, mission planners and data syncing, Earth time is still the gold standard, which means Martians will live on 2 clocks for a while. Earth-coordinated time for communication, and Martian soul time for local life. That's going to be weird. Imagine getting an email from Earth that says, "Let's Zoom at 3 PM, and having to figure out what sol that lands on. Imagine celebrating a birthday on 2 calendars, or setting your oven to bake for 45 Earth minutes in a habitat that runs on Mars seconds. You can't escape the complications of timekeeping, no matter which planet you're on. And here's a subtle but eerie thought to sleep on. The blue sunsets on Mars. They aren't just beautiful, they're slower. Because of the dust in the atmosphere and the shape of the planet, Martian sunsets linger. Light bends differently, colours shift. It's like time pauses, stretches, sighs, and when it's finally night, the sky looks almost familiar, but the constellations are just a little off. And there's Earth, hanging like a pale blue dot. Not the centre of time anymore, just another point on the dial. So you settle in, Martian calendar flickering softly on your wrist, Sol 348, week 49, month, well, we'll name it later. Time here is slower, it drifts, it refuses to conform, but it still ticks. And someday soon, humans will build lives here. Clocks, habits, holidays, maybe even Mondays. and they'll look back and laugh at how we tried to stretch Earth time across the stars. Because Mars isn't late, it's just on Martian time. You wake up but something's off. The light filtering through the blinds doesn't match your memory of morning. The air feels artificial, like it was rendered rather than breathed. You glance at the clock but the numbers flicker, glitch, and reset. The second hand jitters. Time doesn't feel like it's moving, it feels like it's being calculated. Welcome to the head-spinning idea of simulated time, where the clock doesn't tick because of physics, but because someone programmed it to. This is the deep end of the metaphysical pool, where philosophers, computer scientists, and physicists gather to ask the kind of question you're not supposed to ask after 10 p.m. What if none of this is real? We're talking, of course, about the simulation hypothesis, the idea that we might be living inside a highly sophisticated computer simulation. You, me, the stars, the laws of nature, all simulated, all part of a vast program running on someone else's hardware. And if that's the case, then time as we experience it might not be real either, or at least not fundamental, not universal, just a part of the code. Let's slow walk into this. The simulation hypothesis isn't just science fiction anymore. Philosophers like Nick Bostrom have popularized it with startling logic. His argument simplified goes like this. 1. It's very likely that intelligent civilizations will eventually develop technology capable of running ultra-realistic simulations of consciousness. 2. If such simulations are possible, there could be billions or trillions of them. 3. Therefore, statistically, it's more likely that we're in one of those simulations than in the original base reality. Fun bedtime thought, right? But let's bring it back to time. In a simulated universe, time doesn't need to flow like it does in ours. It might not flow at all. It could be computed tick by tick, frame by frame, only as needed. The simulation could pause when no one's observing, or skip ahead, or loop back. Just like a video game loads environments only when you enter them, a simulated universe might process time only when and where it's relevant. Historians still argue whether early mythologies, gods as architects, reality as illusion, were humanity's first brush with simulation thinking. The idea that what we experience isn't real in the traditional sense is older than digital circuits. The Hindu concept of Maya, the Platonic cave, even Descartes' evil demon thought experiment, they're all early versions of this same unsettling curiosity. Now let's talk about clocks. In your reality, clocks tick because of vibrations, oscillations, and movements. But in a simulation, a clock might tick because a loop in the program tells it to. Seconds, minutes, and hours could be entirely arbitrary, coded in for the sake of user experience, not because they represent real physics, but because we expect them to exist. And maybe that's true for all of our physics. Maybe the speed of light is just a bandwidth cap. Maybe quantum randomness is just what happens when the simulation doesn't bother rendering the outcome until you look. Maybe Planck time is the simulation's frame rate. You're not alone in wondering. In fact, some physicists have actively tried to test whether the universe is simulated. One proposed idea? Looking for pixelation in space. Evidence that there's a smallest possible unit of distance, like pixels in a digital image. Others suggest looking for inconsistencies in cosmic ray distributions, which might hint at limitations in a simulated rendering engine. So far, no definitive evidence, but no way to disprove it either. And here's your fringe detail for the night. Some have suggested that déjà vu, those strange hiccups of familiarity, might be the result of simulation glitches, momentary loops in consciousness, or memory caused by computational overlap. Like when your game stutters for a frame and the character blinks twice. Sounds silly? Sure, but it's no stranger than time itself. Because even in this simulation, or reality if you prefer, time already behaves weirdly. It stretches under gravity, slows at high speed, might not even exist at the quantum level. So how different is that really from a world where time is being computed, not experienced? Let's zoom out again. Imagine a computer, massive, planet-sized, maybe star-sized, running trillions of simulations across endless virtual timelines, some with different physics, some with no physics at all, just rules, code, complexity. In one of them, a planet forms, life evolves, civilizations rise, and eventually someone lies awake in the dark wondering if time is real, that someone might be you. But here's the twist. Even if you are simulated, your experience of time is still subjectively real. You feel it. You age. You forget. You wait. You remember. Your days have shape. Your life has rhythm. Real or not, it's the only kind of time you get. So you sip your tea. You wait for the sun to rise. You remember that one embarrassing thing from 8th grade. And time moves, if not because the universe demands it, then because the program does. And that makes the simulation, if it is one, incredibly convincing. Maybe it's not about whether time is real or computed. Maybe it's about whether time matters. And right now, as you lie here drifting gently towards sleep, you realize something. If time is simulated, it's beautifully done. It's consistent enough to trust, strange enough to study, and unpredictable enough to make life interesting. Maybe time isn't an accident of the universe. Maybe it's the feature. So close your eyes, let the processor cool, let the simulation run. You've got time. You're standing in a laboratory now. Sleek, quiet, maybe a little too clean. There's the gentle hum of cooling systems, the occasional click of a keyboard, and nestled behind layers of vacuum chambers and magnetic traps is the most precise timekeeping device ever built. No ticking, no hands, just atoms, light, and a concept of accuracy so extreme it might break our understanding of the universe. Welcome to the age of the quantum clock, if atomic clocks, those cesium vibrating marvels we talked about earlier, set the gold standard for modern time, then quantum clocks are whatever comes after platinum. They're so precise that they don't just measure time, they challenge it. They whisper to physics, "Are you sure about those rules?" Let's start gently. Traditional atomic clocks work by measuring how often atoms of cesium-133 oscillate when exposed to microwave radiation. Remember? 9,192,631,770 ticks equals 1 second. It's specific. It's stable. It runs GPS, the internet, financial markets, and your phone's weather app. But scientists being scientists, they asked, can we do better? Enter the optical lattice clock, a kind of quantum clock that uses atoms like strontium or terbium, which oscillate hundreds of thousands of times faster than cesium. Instead of microwaves, they use visible light, much higher frequency, much finer resolution. If cesium clocks are analog radios, optical clocks are Ultra HD lasers. And these clocks are so accurate they would lose less than 1 second over the entire age of the universe. Not hyperbole, not marketing, just numbers. We're talking about precision at the level of 10 to the minus 18th seconds. That's a decimal followed by 17 zeros and then a 1. If time had an Instagram, this is the kind of clock that would break it. But it's not just about bragging rights. These clocks are sensitive to everything. Move them a centimetre upward, gravity changes slightly, and the clock ticks faster. Warm up the room. The atoms jiggle more and time shifts. Even electromagnetic noise, quantum fluctuations, or tiny changes in fundamental constants can affect their rhythm. Yes, fundamental constants, as in the deep baked-in values of the universe we thought were unchanging. Constants like the fine structure constant, which defines how electromagnetic forces behave. Quantum clocks are now so precise, they might soon detect if that constant isn't. Historians still argue whether we'll look back on this era of precision clocks as the moment physics turned a corner. Because if these clocks find inconsistencies in nature's constants, it could mean that our whole understanding of reality needs an upgrade. Like discovering your GPS has been off by just a millimetre, except it leads you to an entirely different theory of everything. Let's detour briefly into what that actually means. If a fundamental constant changes, even slightly across space or time, then the laws of physics aren't quite as universal as we thought. Gravity might work differently at the edge of the cosmos. Electrons might have behaved a little strangely 10 billion years ago. Time itself might not tick the same way across the universe. Quantum clocks could be our first real way to test that. One current research goal is to place two identical quantum clocks far apart, say, one on Earth and one in space, and compare them over time. If even the tiniest discrepancy shows up, it could reveal shifts in dark matter fields, gravitational waves, or more exotic physics hiding in the background of reality like static on an old TV. Quirky fact to drowse on: quantum clocks are so sensitive, they could even detect the tidal movement of underground water, not the ocean, not rainfall, literally the sloshing of aquifers beneath your feet, because that subtle change in Earth's mass distribution affects gravity, and gravity, of course, affects time. It's not just physics, it's geophysics, with a clock. So how does a quantum clock work exactly? Imagine a trap. Not the scary kind, the laser kind. Scientists use lasers to trap a cloud of atoms in place. Then they zap those atoms with more precisely tuned lasers to make them vibrate between energy levels. These vibrations happen at optical frequencies, which are way higher than the microwave frequencies used in older atomic clocks. Then, using something called a frequency comb, which honestly sounds like a futuristic hairbrush but is really a way to count light pulses, they translate those optical ticks into something we can measure. What you get is a timekeeping device that doesn't just tell time, it defines it at an entirely new scale. But here's the twist. At this level of precision, quantum uncertainty creeps in. You can't observe these atoms without disturbing them, just like in any good quantum story. The more precisely you measure one aspect of their behaviour, the fuzzier another becomes. You're chasing perfection on the edge of unpredictability. And yet, the clocks still tick, still whisper, still reveal things we didn't know we were missing. Some researchers are already dreaming bigger. Maybe future quantum clocks will help us map dark matter, or monitor the slow shifting of tectonic plates in real time, or act as early warning systems for earthquakes, all by detecting microscopic changes in the passage of time. But perhaps the strangest part of it all is this: the more precisely we measure time, the less certain we become about what time is. It's no longer just a human invention, or even a cosmic rhythm. It's now a probe, a tool, a microscope for examining the deepest structure of reality. The line between ticking seconds and quantum fields is getting blurry. You lie back, listening to the hum of lasers and the heartbeat of atoms trapped in invisible cages. They're ticking in ways your brain can't perceive. Not seconds, not minutes, just pure, uninterrupted frequency. Time isn't just being told, it's being exposed. And while most of the world goes on, measuring hours with smartphones and wall clocks and gut feelings, somewhere in a quiet lab, a tiny vibration flickers with the precision of the universe itself. Quantum clocks don't just count time, they question it. You're walking through a corridor now, long, dimly lit, lined with clocks that run in different directions. One moves forward, another ticks backward. A third spins in confused little loops, like it's stuck buffering reality. There are signs pointing ahead. Time travel, they say. But then there's a small note underneath. Permitted, but only in one direction. That direction? Forward. Let's tiptoe carefully into the curious realm of time travel. A place where physics shrugs, fiction cheers, and your deepest wish to go back and fix that one awkward moment in 7th grade still ends in disappointment. Because here's the sobering truth. Travelling forward in time is allowed. You do it constantly. Right now, you're slowly slipping from one second to the next. Your body aging, your tea cooling, your shows falling off streaming platforms. It's not glamorous, but it's legit. And here's the cool part, you can speed it up. Remember that little thing called time dilation? If you hop aboard a ship travelling at near light speed, time will move slower for you compared to everyone else. So when you come back, everyone else will have aged more. You've leapt into their future. This is the kind of forward-only time travel we've already proven. It's real, it's measurable, it's been demonstrated with atomic clocks on airplanes, in orbit, and in high-speed particles and accelerators. The faster you go, the slower your internal clock ticks, and that means you arrive in the future relative to others. Not dramatic enough? Okay. Say you travel at 99.999% the speed of light for what feels like 5 years to you. When you return, hundreds of years could have passed on Earth. Everyone you knew is gone, replaced by skyscrapers, hover pigeons, and vending machines that know your deepest fears. You've time-travelled, no wormholes, no flux capacitors, just relativity. Historians still argue whether H.G. Wells' The Time Machine was the first true depiction of time travel in fiction, but it remains one of the most influential. Wells imagined time as a navigable landscape like space, but in physics, that's only partly true. See, going backward is where things fall apart. Most laws of physics are time-symmetric. That means they work the same forward and backward. A video of two particles colliding looks plausible in reverse, but in reality, macroscopic time, the time you and I live in, is not reversible. Thanks again to entropy. Entropy increases, that's the rule. Eggs crack, not uncrack. Buildings collapse, not reassemble. Ice melts, and so do relationships. The arrow of time only points one way, toward more disorder. Backward time travel? That's like trying to unscramble an egg with the power of positive thinking. Still, theoretical physics allows for a few loopholes. The most famous? Wormholes. According to general relativity, if space can be curved, then maybe, just maybe, it can fold over itself, creating a shortcut between two distant points in space-time. These are wormholes, tunnels through the fabric of the universe, and in theory, if one end of a wormhole experiences time differently, say, by sitting near a massive gravitational source, the two ends could become temporally misaligned. Walk through and boom, you've travelled back in time, except there's no evidence wormholes exist. We haven't found one, built one, or even seen indirect proof of one. And even if we did, keeping it stable would require something called negative energy or exotic matter, which might exist or might not, or might be the physics equivalent of fairy dust. And even if you could build one, every physicist and their cat warns about causality. The moment you go back in time, you risk breaking cause and effect. Save your grandfather from danger, and maybe you're never born. This is the famous grandfather paradox, and it's the narrative death trap of almost every time travel movie. Some theories try to fix this with many worlds logic. If you go back and change something, you don't change your past. You just create a new branch of reality where that change exists. You're now living in a parallel universe where your actions had consequences, but your original timeline remains untouched. Like cosmic forking, still messy, still unproven, still gives philosophers headaches. Here's a strange but real example. In 2000, physicist Ronald Mallet proposed a device using circulating laser light to twist space-time in a way that might allow information to travel back in time. It's theoretical, it's tiny, and if it works, it would only allow time travel from the moment the machine is turned on, no further. Meaning, you can't go back to 1997 and stop yourself from getting that frosted tip haircut. And maybe that's a good thing. Even if backward time travel were possible, it opens up a universe of trouble, causal loops, paradoxes, information appearing out of nowhere. If you receive blueprints for a time machine from your future self and then build it and send them back in time, who wrote the blueprints? These are called closed time-like curves, and they break our intuitive understanding of time. They're allowed in Einstein's math, but not in our sense of logic. They're like time getting stuck in a thought spiral. And let's be real, if backward time travel were possible, wouldn't we have met someone from the future by now? Wouldn't there be tourists in silver jumpsuits taking selfies during major historical events? Or maybe they're really good at hiding. Maybe they only show up at boring times. Maybe they're here right now, politely listening to this sleepy monologue, waiting for the skip ahead button to unlock. So what does all this mean? It means time travel is real, but mostly in the forward direction. It's baked into the structure of the universe. waiting for us to reach high enough speeds or deep enough gravity wells. But backward time travel? That's still a locked door, one with a sign that says, proceed with caution, and a physics degree. And yet, we still imagine it. Every time we wish for a do-over, every time we replay a memory and imagine it going differently, we're time traveling in the only way we truly can, through consciousness. You can't jump back in time, but you can remember, regret, revisit, and maybe that's enough. So for now, let time carry you forward, slowly, gently, with no paradoxes required. Let your dreams handle the rest. You're drifting now, no longer through theories or paradoxes, but through time itself. Not the abstract kind, not simulated or stretched or reverse engineered, just good old-fashioned cosmic aging ticking away in deep space like a whisper through the stars. This is where we try to pin down the most deceptively simple question of all. How old is the universe? You've probably heard the number. 13.8 billion years is practically famous, like a celebrity whose only role is existence. But for such a crisp, specific figure, it hides a messy trail of observations, math, telescopes, background radiation, and a little bit of cosmic guesswork, so let's back up. Or rather, let's zoom way out. The universe as we know it began with the Big Bang, not an explosion in space, but an expansion of space itself. A blistering, hot, dense singularity ballooning outward, setting everything in motion. Particles, forces, light, and yes, time. But how do you actually measure how long it's been since that moment? The trick is looking at light, specifically how long it's been travelling. The farther away something is in space, the older the light we're seeing from it. When you look at a star 1,000 light years away, you're seeing it as it was 1,000 years ago. Telescopes are time machines, quiet, glowing portals that let us peer into the past simply by collecting photons. And when we peer far enough, we see the cosmic microwave background, CMB, that afterglow from the moment the universe first became transparent, around 380,000 years after the Big Bang. That light has been travelling toward us for billions of years, stretched and cooled by the expansion of space, and it's how we estimated the universe's age in the first place. By measuring the temperature fluctuations in the CMB, mapping the distribution of galaxies, and watching how fast the universe is expanding, scientists landed on that magic number, 13.8 billion years. But, and you knew there'd be a but, didn't you? There's a problem brewing in the cosmos, a quiet disagreement, a cosmic scandal whispered among observatories and conference calls. It's called the Hubble tension. Named after the Hubble constant, which describes how fast the universe is expanding, this tension arises because two major methods of measuring that rate give different answers. 1. When we look at the early universe, like the CMB, we get one value for the Hubble constant. 2. But when we measure the expansion of galaxies in the local modern universe, we get a different, slightly higher value. That discrepancy, small but significant, means that our estimate of the universe's age could be off. Some results hint that the universe might actually be closer to 12.6 or 12.7 billion years old, not 13.8. Historians still argue whether this tension is a measurement error, or if it means something deeper, like new physics we haven't yet uncovered. Dark energy, early inflation models, or even changes in how gravity behaves on a cosmic scale. Whatever the reason, the universe might be fudging its birth certificate just a little. Meanwhile, you might be wondering, what's the oldest thing we've ever seen? Well, the most distant galaxy confirmed so far is GN-Z11, which we see as it was just 400 million years after the Big Bang. That's like watching baby photos of the universe. Tiny, chaotic, and glowing red from its sprint through space. But that's just light. What about stuff? What about the oldest things still around? We've spotted stars that are nearly as old as the universe itself, some more than 13 billion years old. These ancient stars found in the Milky Way's halo and in distant dwarf galaxies are like cosmic antiques, quietly orbiting with the wisdom of ages. Then there's M4, a globular cluster filled with some of the universe's earlier stars, sitting about 7,000 light-years from Earth. One of its stars, nicknamed Methuselah, has sparked debate for years because it appears, under certain models, to be older than the universe itself, which, obviously, is a problem. Spoiler, it's probably not actually older than the universe. The age estimates just push the limits of our measurement techniques, our stellar evolution models, and our assumptions. But it's a good reminder that even in science, certainty comes with error bars. And what about us? How do we fit into this cosmic timeline? If the universe is 13.8 billion years old, and Earth is around 4.5 billion, then we showed up fairly late to the party. Multicellular life didn't emerge until about 600 million years ago. Humans, a mere 200,000 years, less than a blink. And clocks, calendars, we've only been recording time for a few thousand years. That's like arriving in the last second of a 24-hour movie and trying to summarize the plot based on a single freeze frame. But that's what makes cosmic time so humbling. It reminds you how much came before you and how much will come after. The Earth will outlive you. The Sun will outlive the Earth. The galaxy will swirl on long after the Sun becomes a memory. And the universe, it will keep aging, expanding, cooling. But we're not at the end. Not yet. You're still here, spinning through a cosmos that's almost 14 billion years old and somehow still in progress. So the next time you check your birthday or read the year on a document, remember, you're not counting from the beginning of time. You're just counting from a tiny blip in a much longer story. And the true cosmic calendar, it's still ticking. You're standing on the final page of a very long book, the kind with no cover, no title, and just one sentence per billion years. You flip ahead, but the pages grow thinner, colder, and dimmer. The words start to fade. The plot slows down. You're gazing into the end of the story, not of you, not of Earth, but of time itself. Because yes, time might end. It's not a popular topic at parties, but the universe has several possible endings, and in most of them, time as we know it simply stops making sense. No more ticking, no more entropy to increase, no more events to mark the passage from one moment to the next. Let's ease into the possibilities. The most widely discussed scenario in modern cosmology is called the heat death. Despite sounding like a very intense sunburn, it's actually the coldest, most boring way the universe could die. Here's the idea. The universe keeps expanding. Galaxies drift farther apart, stars burn out, black holes evaporate, and over trillions upon trillions of years, everything just fades. Energy spreads so thin that no meaningful processes can occur. No light, no motion, no temperature difference. And without change, there's no way to mark time. It doesn't stop exactly. It just becomes meaningless. Like trying to measure minutes in a room where absolutely nothing happens, ever again. In this frozen void, the universe reaches maximum entropy. It's flat, dark, cold. The cosmic equivalent of a screensaver that's been on for a Google years. Now take a deep breath. We're not there yet. In fact, the expansion of the universe is accelerating, thanks to that mysterious force we call dark energy. It pushes galaxies apart faster and faster, and if it continues unchecked, we get a much more dramatic finale. The Big Rip. Here's how that goes. Dark energy keeps gaining strength. Eventually it overcomes the gravity holding galaxies together, then solar systems, then planets and stars, and then it gets personal. It rips apart molecules, then atoms, then the fabric of space-time itself. In the final fractions of a second, even time stops ticking. Not because it runs out, but because space-time ceases to exist. You can't measure time in a reality where distance and duration have no meaning. The clocks don't break, they just have nowhere left to be. Historians still argue whether this scenario is likely, or whether dark energy might mellow out with time. Some think it's a temporary phase, others see it as the universe's foot steadily pressing the cosmic accelerator. Then there's the gentler cousin of doom, the big freeze. This is like heat death but slower. Everything continues expanding forever, but with a little more dignity. Stars die, galaxies drift into isolation, and the universe becomes a graveyard of embers. Over the next 100 billion years, black holes slowly radiate away via Hawking radiation, shrinking until they vanish in tiny bursts. And then, nothing. No heat, no particles, no photons, just a dilute soup of low-energy radiation, drifting through a space-time with nothing left to say. And again, time loses its meaning. Not because of drama, but because of stillness. Of course, there's a wildcard ending too, the Big Crunch. This was once a favourite among cosmologists. If the expansion of the universe ever slowed down, gravity could pull everything back in. Galaxies, stars, and eventually all matter would collapse into a single point, like a reversed Big Bang. Boom! The end. Or maybe the beginning again? Some theories suggest that after a big crunch, a new universe might explode outward in a fresh Big Bang. A cyclic model, where universes rise and fall like the tide. In that model, time is reborn. It doesn't end, it just loops. And here's your weird fringe fact of the night. There's a theory called conformal cyclic cosmology, proposed by physicist Roger Penrose, which suggests that the end of one universe can become the beginning of another, not through a collapse, but through a kind of mathematical flattening. As entropy reaches infinity, it circles back around to zero. The universe doesn't reset, it just becomes indistinguishable from the next one. Time doesn't end, it forgets. And then, of course, there's the ultimate we have no idea ending. The universe might decay into a quantum vacuum, spontaneously collapsing into a lower energy state at the speed of light. No warning, no pain. One moment, you're brushing your teeth. The next, reality's operating system gets replaced and time as we know it just blinks out. So, if time can end, what does that say about all the time you've lived? All the clocks and calendars, all the moments you've measured, all the days you've waited through and the nights you've tried to forget. It says they were real, even if temporary. Even if the timeline ends, it doesn't undo the pages that came before. Because in every version of cosmic death, the past remains. In memory, in radiation, in the stretched and faded echoes of light from stars long gone. The universe may forget to tick someday, but it won't forget that it once did. And here's a quieter thought to carry with you as the clock softly hums. The end of time doesn't mean the end of meaning. Even a finite timeline is long enough to contain wonder, love, curiosity, whatever it is that keeps you listening this far. The universe might stop counting, but for now, it hasn't. So close your eyes. You're still inside the story. You're lying in bed, half awake, and suddenly a strange sensation washes over you. That feeling you've been here before, this moment, this smell, that flickering shadow on the wall. It's uncanny. Déjà vu, they call it. But tonight we're going deeper than that. Because in this dream space between consciousness and sleep, your mind is dancing through time loops, causality tangles, and paradoxical whispers from the farthest corners of physics. Here, time doesn't just move forward, it swirls, bends, maybe occasionally even folds back on itself. We've talked about entropy, relativity, and quantum clocks, but now we tiptoe into the fringe. Can time loop? Can cause follow effect? Backward? And are you stuck in a timeline, or are you just choosing one of many? Let's start with closed time-like curves, CTCS. This is the theoretical name for a loop in space-time, a path that brings you back to the exact same moment from which you began. Think of it like a racetrack, but instead of going around in circles, you're going around in time. The equations of general relativity do allow these paths under certain extreme conditions, like near spinning black holes or in hypothetical structures like wormholes. So yes, in theory, the laws of physics don't prohibit time loops, they just make them really, really inconvenient. Now remember that grandfather paradox? You go back in time and accidentally prevent your own birth. Classic. In a looped timeline, this becomes a problem. If your actions in the past prevent your future, how did you go back in time in the first place? Here's where physics gets clever. Some interpretations suggest that time loops self-consistently resolve. In other words, the universe won't allow paradoxes. If you travel back in time, everything you do already happened in that timeline. You can't change the past, you were always part of it. This is called the Novikov self-consistency principle. So if you go back and try to smash your grandfather's alarm clock so he misses a date with your grandmother, something will always happen to stop you. The hammer breaks. The clock is a fake. A passing goose distracts you. Whatever it is, the timeline resists contradiction. It's like the universe has a built-in nope button. Historians still argue whether this kind of causal self-protection is comforting or horrifying. On one hand, it prevents paradoxes. On the other, it implies free will might be an illusion, at least when time travel's involved. But what about déjà vu? Some fringe theories tie it to temporal overlap, a brain-level hiccup that makes you feel like you're remembering the present. Or, if you're feeling whimsical tonight, perhaps it's a brief crossover from a parallel timeline, a glitch, a memory from a moment you didn't quite live through, except somewhere, some version of you did. And that leads us to the multiverse. The many worlds interpretation of quantum mechanics says that every possible outcome of every event actually happens in some parallel reality. When you choose tea instead of coffee, there's another you who made the opposite choice. Every coin flip, every sneeze, every left turn on your way home, each branches the universe into a new timeline. If that's true, time doesn't just loop, it branches like an endlessly growing fractal. You're not in a single straight line. You're riding a wave of constant decision forks, a timeline of infinite yous heading in infinite directions. So maybe déjà vu isn't a glitch. Maybe it's just your brain brushing up against the echo of another timeline. A place where this moment already happened, almost exactly the same, but with a different ending. There's another version of this theory called the block universe, which we touched on earlier. The idea that all moments in time, past and future, already exist. You're not moving through time, you're moving through your perception of time. In this model, time is a static landscape. The future isn't being written, it's already there. You just haven't gotten to that page yet, which means loops, jumps, skips, déjà vu, they could all be your consciousness navigating the block, not just passively living it. And now let's talk about the quantum weirdness of retrocausality. In standard physics, cause leads to effect. That's the deal. But in certain quantum interpretations, effect might influence cause, at least at the microscopic level. Some experiments suggest that a particle's future state can affect how it behaved in the past. No one's rewriting their baby photos yet, but the implications are wild. In these models, time becomes a two-way street, at least in certain circumstances. It doesn't mean you can uneat a burrito, but it might mean the universe's deepest rules don't draw such a strict line between before and after. Even in your brain, time is fuzzy. Neurologically, your perception of time is a construction, not a measurement. Your brain edits events for narrative flow. It delays what you perceive to make sense of movement. It inserts false memories, corrects inconsistencies, and sometimes, even if just for a second, it replays the moment. Déjà vu might be a misfire in short-term memory, or a glitch in hippocampal pattern recognition, or the brief overlapping of two perceptual channels that weren't meant to sync, or maybe, just maybe, it's a tiny hiccup in a looped slice of time, a moment that wants to repeat. So what would a world look like if time did loop? Imagine a universe where entropy resets, where heat death is followed by a new Big Bang, where you live, die, and are reborn infinitely, not reincarnated but repeated, like a vinyl record stuck on one beautiful groove. Some physicists suggest that under certain cyclic models the universe might bounce, expanding, collapsing, and then expanding again, forever. In each cycle, time restarts, maybe with changes, maybe not. Maybe this isn't your first ride. Maybe that explains your uncanny dreams, your feelings of prediction, the moments that feel too familiar, because time isn't always a line. Sometimes it's a circle, a spiral, a Mobius strip. And you? You're the traveller. You loop back, you drift forward, You feel echoes of choices made and unmade. So close your eyes. Let the moment repeat. You've been here before, and you'll be here again. You're standing at the edge of something now. Not a cliff, not a calendar, not a watch face, but the idea of time itself. Everything you've travelled through so far, light and gravity, clocks and calendars, dreams and déjà vu, it's all led here. To the big question, whispered in every tick of every clock, does the universe have a clock? And now, finally, with all the sleepy science behind you, we're going to answer it. Sort of. First, let's step back and ask, what would it even mean for the universe to have a clock? We don't mean a giant stopwatch floating in the void, counting down to some cosmic deadline, though that would at least make holidays easier to plan. We mean something deeper, a fundamental rhythm woven into the fabric of existence, a built-in metronome, something absolute, something universal. Let's review the suspects. Atomic clocks? Impressive, yes, but they're human-made, local, and deeply affected by motion and gravity. They give us time that works, but not necessarily time that is. Cosmic expansion? That's a candidate. The universe is growing. The space between galaxies stretches. Maybe the expansion itself is the ticking of a cosmic clock, each second defined by how much space expands between ticks. But here's the problem, that expansion is accelerating. The ticks aren't evenly spaced. There's no universal tempo. It's not a drum beat, it's a slide. Entropy? Our old friend. The arrow of time. The reason you age, coffee cools, and socks disappear. It points us forward, but it's not a clock, it's a direction. There's no unit of entropy. No hands that sweep. It's a slope, not a stopwatch. Quantum time? There's Planck time, the smallest meaningful unit of time in physics, about 5.39 times 10 to the negative 44th seconds. That's unimaginably fast. It's the theoretical frame rate of the universe, below which time becomes meaningless. If the universe has a clock, maybe that's the tick. But there's a catch. Quantum mechanics doesn't actually require time to be fundamental. In some formulations, especially in quantum gravity and theories like loop quantum gravity, time emerges from more basic, timeless principles. In these models, the universe doesn't have a clock, it becomes one. Let's slow that down. The idea here is that time isn't baked into the universe's source code. It's a side effect, a property that shows up only when systems reach a certain level of complexity, like temperature, or flavor, or sarcasm. In some theories, the universe at its most fundamental level doesn't evolve in time. It just is, a timeless web of relationships between quantum states. When we zoom out, those states appear to change. We call that change time. But at the deepest level, nothing is moving. There are no ticks, just structure. Historians still argue whether Newton's idea of absolute time, a universal clock that ticks the same for everyone, was ever real, or just a convenient assumption. Einstein shattered it. Quantum mechanics complicates it. And general relativity turns time into a bendable, stretchable coordinate that depends on where and how you observe it. So maybe the question isn't, does the universe have a clock? Maybe it's, why do we need it to? Here's a thought to settle into. Perhaps clocks aren't for the universe. Perhaps they're for us. To anchor our experiences, to give shape to change, to remember when things happened and how they made us feel. Time lets you tell stories. Without it, there's no before and after, no cause and effect, no first kiss, no bad haircut, no last look. You just float through an unmarked sea of experience, with no way to tell whether anything mattered. A clockless universe may still exist, but a clockless life? That's harder to imagine. And here's your quirky fringe fact for the road. In 2021, physicists built a quantum clock using a pair of entangled atoms, where time emerges only from changes in correlations between the atoms. It had no pendulum, no frequency, no traditional mechanism. It measured time without time, just change, and maybe, at the most cosmic level, that's all time ever was. a way of keeping track of change. No tick-tock, just difference, just motion, just becoming. So when we ask whether the universe has a clock, maybe what we're really asking is there something deeper holding all this together? Some rhythm beneath the noise? Some cosmic heartbeat? And the answer, drifting softly through every expanding galaxy and cooling star and flickering brainwave, is maybe, or maybe it's you. Maybe you're the clock, ticking through the universe, counting the seconds with your thoughts, measuring the cosmos by the changes in your own story. If the universe has a clock, it doesn't hang on a wall. It pulses inside you, and right now it says, sleep.